This is problem 7.89, it's on page 406. The beam AB supports the uniformly distributed load of 1,000 newtons per meter and two unknown forces, P and Q. Knowing that it has been experimentally determined that the bending moment is negative 395 newton meters at A and negative 215 newton meters at C, determine first of all P and Q and then draw the shear and bending moment diagrams. I did both at once. Let me show you why. Let's just start off by looking at the beam. So there's the wall support, the beam is off to the right, Q acts out at the end as a point load, and P acts at 0.25 meters from Q. The 1,000 Newton per meter load acts up to P, and there are a couple of points indicated, 0.2 meters to point C, 0.2 meters further to point D, point B is out here, and point A is there. So the first thing I did is I noted that the moment at A is negative 395 Newton meters, and the moment at C that was given was negative 215 Newton meters. Okay. So what I decided to do is just go ahead and make a free body diagram of the beam. In fact, let's do that off to the right. That way I can put my shear moment diagrams beneath the beam. So make a free body diagram of the beam with P and Q here, the distributed load of 1,000 newtons per meter along the length, and then the reaction at A and the moment at A could be written in terms of the information we've been given. So the reaction at A would just be counteracting all these loads. So P plus Q plus 1,000 newtons per meter times 0.4 meters worth. I guess I didn't add that to the diagram, but if we have 0.4 meters worth, well, that's 400 newtons. So plus 400 newtons. That's the reaction at A, right? Just from summing forces in the vertical direction. The moment at A, well, now we need the moment of all this. So notice that 400 newtons is the resultant of the 1,000 newton per meter load, because again, we've only got 0.4 meters worth. So the moment at A has to counteract all these, so it would be what? P times 0.4 meters plus Q times the entire length, 0.2 plus 0.2 plus 0.25 is 0.65 meters, plus the 400 newtons acting at 0.2 meters, because that's where the resultant would act. Okay? So there's the moment at A in terms of P and Q. Now that's convenient because the moment at A was given as 395. Now we have to think about this a little bit more deeply. Let me go ahead, like I said, and draw the shear moment diagram. So let's not forget the reaction at A. Let me put it in a different color. The reaction at A and the force reaction is P plus Q plus 400, and the moment reaction at A is, let's see, well, 0.2 times 400 would be what, 80? So that's just 80 plus 0.4 P plus 0.4 Q. Okay? Now, let's consider the shear and moment diagrams so we can understand how all of this works together. So the shear diagram in newtons will look something like this. There's X in meters, position along the length of the beam. Try and line it up as usual. We know that the shear has to begin at the reaction of P plus Q plus 400. That's the reaction at the beginning, so that's what shear must be in the beam to counteract that reaction. But then the distributed load decreases the excuse me, amount of shear required by 1,000 newtons per meter, but we only have 0.4 meters worth. So 0.4 times 1,000 is 400 newtons. So the shear must decrease by the time it gets to D down to P plus Q plus 400 minus 400. So this would just be P plus Q. At point P, notice that the load will have to decrease by P. So the value of the shear comes out to just Q. And as we go along, eventually we have load Q, and we go back down to 0. So P is just this distance, just like Q is that distance. Okay? Or if you like, just look at the labels on the axis. Okay? So there's the shear diagram. Now the moment diagram is just, well, let's see. We'd have to start with the moment at A, which we know the moment at A is negative 395 Newton meters. That's the moment at A. We actually also know the moment at C. Now notice that C is halfway between points A and D. So this point is at negative 215, right about there or so. And if you look at the way the area is displayed, well, there's more area adding up at the beginning than at the end. So this must be a concave down type of curve. But notice it continues concave down through point C and all the way up to point D. Okay. From there, notice that the area is just the area of a rectangle, and the slope would just be Q, because the shear represents the slope of the moment graph. So the slope is just Q. And how much change is there in all of this? Well, it's pretty easy to see that the change in the moment from here to here, well, that's not very good. Try again. So from the very bottom of the moment curve to the very top, the end where we should come out to 0 because there's no moment at the end of this beam, that change in moment has to be 395 Newton meters. But we also know that that change in moment is equal to all of these areas added up, right? But we already know that it has to be equal to this. Let me prove it to you. So the area beneath this curve would be P plus Q plus 400 plus P plus Q divided by 2. What am I doing here? I'm taking this height and finding an average height. That's all I've done so far. So I'm taking an average, I'm converting a rectangle and a triangle into just a simple rectangle. So I found the average height, and now I'm going to multiply it by the width, 0.4 meters. Okay. That's the area of this section. And then we've got this area to contend with as well, which is simply Q times 0.25. So plus Q times 0.25. This will begin to look familiar in just a second. Let's move up. Okay. So 395 equals what? Well, if you look at all the constants, we've got 400 over 2, well, that's 200, times 0.4. Well, 10% of 400, let's see, let me think and make sure I've got this right. Yeah, that should work. Let's think it through. So 400 over 2 is 200. 10% of 200 is 20. 20 times 4 is 80. So sure enough, we get 80. So that takes care of the 400. Notice there's a PQ, so that's 2P, 2Q, right? But divided by 2 is just P plus Q times 0.4. I've already multiplied this 0.4 by this. Okay? So that takes care of the rest of this stuff. Now remember, we got 2 P's, 2 Q's, divided by 2 is just P and a Q times 0.4. So there we go. And then we have plus Q times 0.25. Okay, well, let's put the Q's together. So this is 80 plus 0.4 P. And we've got 0.4 Q plus 0.25, so 0.62 or 65 Q. Does that look familiar? It should. It's right here. Actually, it's not. What happened? How did I get more Q out of it? Well, it's not exactly that, but it looks a lot like it, right? We're close. We got the 80, we got the 0.4 P. It doesn't mean that this moment at A is wrong. At least I hope I didn't write that incorrectly. I did write it incorrectly, I'm sorry. What did I do wrong in writing? Fortunately, it's right here. I copied it wrong. I had 0.65 here, I apologize. So I had, I had 400 times 0.2, so 10% of 400 is 40, times 2 is 80, so that's where the 80 came from. I had 40% of P, and I should have had 65% of Q, so that's my fault, I copied it wrong. So let me try that again. So in fact, this does match exactly. 65% of Q, there we go. So I really didn't need to go through all of this area addition. I could have just noted that I knew the total moment at A. Right? Anyway, we can rearrange this just a bit. Take 80 from both sides, you get 315 equals 40% of P plus 65% of Q. Let me call that equation 1. Okay. And all I've done is I've set the moment in A equal to, now you might say, well, what about the fact that there's a negative sign? They gave us a negative sign to indicate that the moment was down on the lower half. It was down here, it was a negative moment. What that really means is that the moment in the material is negative. So let me show you what that means. Let's get rid of this for the time being. You see that the moment at A has to act like this. What they're giving us is the moment in the material. So if you take just a little bit of beam, just a little bit of distributed load, but not enough to make a difference in the moment, can you have any positive moment on the right-hand side? No, it would cause the beam, or that little segment, to rotate counterclockwise. Therefore, we must have a negative moment. And it's the magnitude of that negative moment, as this gets closer and closer to A, that they've given us here at 395. So I just looked at this as a change in moment, and added up the change in moment from the area beneath the shear. Okay, so all this should be consistent. Hopefully that makes some sense to you. Anyway, there's equation 1. What about equation 2? Well, equation 2 will have to come from here, because look, that's where we've got another point. So 215. So we're interested in the change in the moment, let's say here. Okay. So what change in moment do we have there? Well, isn't that just, let's use some human factors psychology here. Isn't this change in moment just this area? So let me call this the change in moment from 0 to 0.2. So from 0 to 0.2, what is that change in moment? It would help if I put the right pin colors on that. Go. Well, we should be able to figure that out. The change in moment from 0 to 0.2 should just be this area. Well, how much area is that? Well, let's see. It'd be, let's see, let me write it all out for you. So I guess I didn't write it all out on my paper. I must have been working on another sheet or something. Anyway, it'd be P plus Q plus 400. That's the value of the shear here. What's the value of the shear here? Well, it's half of the value between those two. So that must be plus P plus Q plus 200 divided by 2. That gives me that average height again, here, multiplied by 0.2, or 0.2 meters. That's this area that we're interested in, the change in moment from 0 to 0.2. So we have what? Let's see, 2P plus 2Q plus 600 all over 2 times 0.2. And I'm going to run into this equation, so let me, I don't want to erase that. I don't really want to erase anything. I guess I've got to sacrifice this. Okay, so let's continue upward with this. This is just P plus Q times 0.2, takes care of these terms. And this would just be plus 600 over 2 is 300, 300 times 0.2. And so that's equal to what? 0.2P plus 0.2Q. And this would be what, plus 60? And the change in the moment we already know is the difference between these two. It's 395 less 215. Well, that's what, 180? 180. And so then if we simplify things further, if we take the 60 to the other side, we'd have 120 equals 0.2 P plus 0.2 Q. And then if we divide that 0.2 back out, I shouldn't have distributed it, I guess. If we divide it back out, then we'll get 600 equals P plus Q. Now this is our second equation. Notice the first equation came from information they gave us about point A. The second equation came from information they gave us about point C. We don't really care about anything else. All we really want is equations 1 and 2 so that we can solve them as 2 equations and 2 unknowns. So we don't really care about all of that. We just care about getting to this point. So, continuing with equation 2, we'd have P equals 600 minus Q, which we can then plug into equation 1. So, equation 1 tells us that 315 equals 40% of P plus 65% of Q. Actually, I should have done it the other way. I'm substituting for P. So 600 minus Q for P plus 65% of Q. Okay. And why did I write through? Oh, 315 came from here. Yeah, we're doing it. All right. So I went ahead and just typed the constants into my calculator. Let's see, 40% of 600 is 240, and then I have minus 40% of Q plus 65%, so plus 0.25 Q as a net effect. Take 240 away from 315, you get 75 equals 0.25 Q, and so Q is 4 times 75, or in other words, 300 newtons. So we need a force Q of 300 newtons, and now we can figure out P. 600 less 300 tells us that P is also 300 newtons. I guess they wanted to give us either scare us that we got the same number or give us a warm fuzzy feeling that they came out the same, and obviously somebody designed this problem. But anyway, if you go back now and you use this P and Q with this load, you will get exactly the moment at A and the moment at C, as well as the reactions that the problem prescribed. And so everything's consistent and all of this works. So that's it. So P and Q are just 300 newtons.